talk. Our speaker is Professor David Krieg. So he will discuss sampling recovery in uniform. Welcome.
Thank you. And thanks very much to the organizers for putting this nice thing up. So I will talk about sampling recovery in the uniform norm and especially also about the related discretization problem of the uniform norm. So what's the problem at hand? So most of what I'm going to tell you is very elementary. So we assume, like in Anthony's talk, so we are given, or let's say we are given some bounded function on an arbitrary set D and some n-dimensional linear space of bounded functions. So B of D should be the space of bounded functions on the set D. Yeah, so if you are more into geometry than sampling recovery, you can just imagine like that D is a finite set and then B of D will just be equal to, well, C to the n. Okay. And the task now is to find some function from the linear space such that the distance to the target function f in the uniform norm is small. Okay, so this would be classical approximation theory, and now the difficulty is, the problem is that we do not know this target function f, and we can only obtain samples of this target function, f of x1 up to f of xm, and we assume that each sample is costly. Yeah, for example, getting such a function value may require you to solve some complicated PDE or to do some physical measurement. So we want to have the m here as small as possible, and those samples can be exact or noisy. And I mostly talk about the exact case, but also a little about the noisy case. Okay, we start with some simple observations. So a very simple and classical result is that there is always a best approximation from the given n-dimensional space. So some function fn in Vn such that the distance is minimized here. And denote the distance by capital E of f to the space Vn in the uniform norm. So this should be the pointwise maximum. Okay. And a simple second of thought tells you that it's in general not possible to find this Fn with finitely many samples. Yeah, of course. For example, if you have like just a few samples and you want Vn is the space of constant functions, for example, then your function could look like this. Your true function, in which case the optimal approximation would be maybe this, or it could just look like this. And the optimal approximation is down here. So no matter how many samples you have, you cannot find the optimal approximation. So hence what we want to do is just find some element in the space Vn such that the distance gives you the optimal approximation up to some factor Cn.
So I interrupt you, but you said that D is a finite set.
This is just an example. In this case, of course, you can do it with finitely many, but I mentioned that the capital N is very large. Yeah. Right. And then this is also not feasible.
No, but then on a finite set, you can find the best approximation.
Yeah, of course, yes. Sure. Yes, and also, if you want only this relaxed optimality condition, then it's also clear that you need at least n samples where n is the dimension of the space, because otherwise, because this here implies that in particular you can recover every function from the space Vn exactly. Yeah, of course. And so we want to know what is the best possible constant in this relation here, provided that you use m samples. Yeah, and as I said, the minimal number of samples that you can do anything is precisely the dimension of the space. So we start with this setting, and in this case it's exactly known what is the best possible you can do with precisely n samples, m equal n, for any n-dimensional space. Namely, there are always, for every epsilon greater than 0 and any n-dimensional space of bounded functions, you can find n sampling points in the domain and some recovery map, which is even linear in this case, such that you can catch the optimal approximation of the space Vn for any target function of bounded functions up to a factor n plus 1. And in fact, the n plus 1 here, you cannot improve it in general. Of course, for some spaces you can improve it, but this is the best you can hope for general spaces Vn. And how do you find such sampling points? Well, those are basically the Fichete points, if you know them. So the task is to find points xk and functions phi in the space such that phi k of xj is just the Kronecker delta and the norm of phi k is close to 1. You can do this by minimizing the gram determinant of any basis over all uniform measures on endpoint sets. Okay. So the next natural question is, of course, can you get an almost optimal approximation here? So can you replace the n plus 1 by some constant if you increase the number of samples? And the answer is yes, if you use exponentially many samples, 9 to the n. So there is this result here, which tells you that for any n-dimensional space, you can find 9 to the n points and a recovery map phi such that you will get the best approximation from the space Vn for every bounded functions up to a factor 5. Okay, how do you find such points? So you can take 1/4 net of the unit ball in the space Vn and take xk as the maximizers of this net. And well, of course, you may say 9 to the n, this is a lot, this is quite bad, but it's just not possible to improve it significantly. So one can show that if you want a constant here on the right-hand side, so quasi-optimality for every bounded function, then in general, a polynomial amount of samples is not enough. Okay, and so now we want to find some way between those two things. So we want to improve this factor n plus 1 with less oversampling, less than exponential oversampling. And here is already the general result. So it turns out that already 2 n samples give you a significant improvement. So same message as we heard already yesterday, a little oversampling can help a lot. So for any n-dimensional space of bounded functions, you find 2n points in the domain. Yeah, in this case it would just be 2n coordinates, such that you can recover with these samples, with these coordinates or whatever, every bounded function up to a factor square root of n times the optimal approximation, times some universal constant. I do not claim that the 60 is somehow optimal. Okay. So this is a pretty elementary result, but it seems that it was indeed new. And what can I say about this? Yes, the square root of n, you cannot replace it by a lower order term. That's not possible. Not even if you use any polynomial amount of samples. And instead of 2n samples, you can get the same still if you use, let's say, 1.1 times n samples, or with any constant oversampling factor, yeah, then of course the 60 will change here, but the square root of n will stay. And since this is not the first result in this direction, let me give you some historical comments. This is, of course, quite incomplete, but here we see that, for example, in a paper by Volodya, there already appears that you can get such an error bound for a nonlinear method, namely the least maximum estimator. Whenever you find points that give you good discretization of the uniform norm. So if you have a constant n times many points such that you can catch with the maximum of these points the maximum norm on the full space of bounded functions up to a factor square root of n, then you can get such a thing as least for a nonlinear method. Yeah? And then there is this result which says that whenever you have a Nikolsky type condition of this form, that the uniform norm is bounded by square root of n times the 2 norm on your space Vn, then you can indeed find such points with this property. Yeah? And it turns out that you can always arrange this condition here, this Nikolsky condition, if you just choose the measure correctly. And this is indeed a very old result from the 1960, which I'm going to show you now. So let's go into the proof. So for any, the first step is this old result from 1960 by Kiefer and Wolfowitz, who show that for any n-dimensional space of bounded functions, you can find a probability measure on the domain such that on the space, the supremum norm is bounded by square root of n plus some epsilon times the 2 norm. So you have this optimal Nikolsky condition for this measure mu. Yes. And if you look into the proof of this, you see that actually it's not just any measure, it's actually a discrete measure with n squared sampling points. Yeah, so this is also already in the direction where we want to go, so we want to discretize the supremum norm. Okay, how do you find such a measure? You find it by, again, by maximizing the Gram determinant, but this time not only with respect to all uniform measures on n point distributions, but with respect to all, let's say, finitely supported probability measures, so with finitely many point atoms. Okay, now we have this measure mu, and the second step is a discretization of the 2 norm, because we already know how to get from the uniform norm to the 2 norm. And here one can show that for any probability measure on D, you can have this one-sided discretization of the 2 norm on the space Vn. So you find 2 endpoints such that the continuous 2 norm is bounded above by a constant times the discrete L2 norm. Yeah, weighted in this non-weighted, but with 1/2 and such that it's a probability measure. Okay. Yeah, and this result in this form we use is from Bartel, Schäfer, and Ulrich, but there are older results in this direction which gives you such a thing already for weighted discretization by Limonova and Temniakov. And how do you find such points? Well, interesting maybe is that you get such a result already for random points, just taking IID with respect to this Kiefer-Wolfowitz measure, if you allow a logarithmic oversampling. So if you take n log n sampling points, then they satisfy this condition already with high probability. And now if you want really 2 endpoints, so without logarithmic oversampling, then you can use a subsampling procedure For example, you can use the one by Watson, Spielmann, and Srivastava from very recently also to find such points. Okay, so if we put those two things together, what do we have? We have that for any n-dimensional space of bounded functions, we now find two endpoints such that we have this strange L infinity L2 discretization. So the uniform norm is bounded by the discrete L2 norm. Okay, so if you're interested in discretization itself, then maybe the following corollary might look more interesting. So in particular, the uniform norm is bounded by square root of n times the discrete maximum. Yeah? And this is again like optimal in general, so optimal in the same sense as before. Okay, so this has to be seen as, yeah, in the context of this very nice series of work recently on the discretization of integral norms, yeah, where for example, there appears such a result again on the Nikolsky condition, which we now know can always satisfy. Okay, and what is now the fourth step? So this is just a unweighted least squares approximation. So what do we do? For those sampling points, we consider just the function which minimizes this discrete L2 norm from the space Vn, and it's a simple lemma to show whenever you have this L infinity L2 discretization that the output of this least squares approximation will be as good as the best approximation up to this factor square root of n. Yeah, in comparison, so we saw before that if you have L infinity discretization, then you can get such a result for the least maximum estimator instead of the least squares estimator, which is nonlinear. If you want something linear, you really need this strange L infinity L2 discretization. So this is somewhat important. Okay, here's a summary of what I did so far. So we want near best approximation from arbitrary n-dimensional space of bounded functions using m samples. And what happens, so if you use less than n samples, then you cannot get close to the best approximation at all. If you use precisely n samples, then you get to the best approximation up to the factor n plus 1. If your number of samples is somewhere between, let's say, 2n and n to the 999, then you get the best approximation up to a factor of order square root of n. And if you use exponentially many, you can get the best approximation up to a constant factor. And so you have some kind of jumpy behavior here. And we do not really know what precisely happens in the intermediate range. So if, for example, you have the number of samples is the dimension plus square root of the dimension, then it has to be somewhere between n and square root of n, but it's not clear how it looks like precisely, or also if you have exponential in square root of n, for example. Yeah. Okay. Yeah, and just so you don't get confused, or just maybe so you get confused. So this is for what the best you can do for general spaces Vn. Of course, if you consider particular spaces Vn, then always the results may be much better. Yeah? For example, univariate polynomials, then you can do much better already with n samples. Or piecewise constant functions are even more drastic. Yes. Okay, and I promised also to say something about inaccurate data, so noisy data. So now we assume that the data is given by the function values plus some noise term, eta k. And since our method uses an unweighted least squares algorithm, it behaves nicely under noise, so you get what you wish for. So for any n-dimensional space and two endpoints, you can find two endpoints and a linear recovery map such that the linear recovery map applied to the noisy data gives you the best approximation up to the factor square root of n plus the 2 norm of the noise. Okay. And let me turn now to the case of approximation in LP, because there already is a very nice similar result for approximation in the 2 norm, namely for any set D and any n-dimensional space, you can find two endpoints such that, and a linear recovery map such that you find the error of the approximation in L2 will exceed the error of best approximation at most by a constant, but the error of best approximation is still in the uniform norm. And you can do this again with a unweighted least squares estimator. Okay, so here I assume some more regularity just for measurability issues. For example, D could be a compact Hausdorff space and Vn a space of continuous function, mu a Borel probability measure. But actually you don't need continuity. But this is a simple way of putting it. Okay. And so how do we get to general LP? Well, you can just take the union of the 2 point sets. And since both point sets for p equal 2 and p equal infinity give you some nice discretization, you can interpolate the discretization to get some LP little l2 discretization. So the LP norm is bounded by the discrete L2 norm times some optimal order factor in the dimension. And then you can just again use the unweighted least squares algorithm with these 4 n sampling points. So that you get for any, let's say, continuous function now, you get that the error of this least squares algorithm in LP is bounded by the error of best approximation in the uniform norm times some optimal order factor in n. Okay.
Was there 1/2 missing in the exponent probably in discretization? It's 1/2 minus 1 over p, right?
Here I take the L2 norm without 1 over n in front. So I think it's not missing now. Yeah. So this should be the standard L2 norm here. Okay. And yeah, let me switch now a little to the worst case scenario. So we want to do worst case estimates. So we assume that we have some model set f, capital F given of continuous function. And now we ask the question, what is the minimal approximation error in the LP norm that you can guarantee only under the model assumption that your function f belongs to the class capital F, and you can use up to n samples. And the answer to this question is given by the sampling numbers. So this is just a definition. So you take the infimum over all sampling points and over all recovery maps phi, and then the supremum of the distance of the unknown function and the output of this recovery over the model set f. So those numbers describe this minimal worst case error. Or maybe also you can consider the linear sampling numbers if you want to restrict yourselves only to functions, recovery maps which are linear. And in comparison, one can consider the Kolmogorov widths of the class F, which are just the best approximation of this class by an n-dimensional linear space. So here we take, again, the worst distance of F to a linear space Vn, and we optimize over all n-dimensional spaces Vn. And what we get from our results is that the linear or nonlinear sampling numbers using 4n samples, they are bounded above by the Kolmogorov widths of the class capital F in L infinity times some optimal order factor in n, so n to the 1/2 minus 1 over p if p is greater than 2. Yeah, and it's optimal in the sense that the result would not be true anymore if I put here any smaller exponent. Yeah, you can see this by considering Sobolev spaces of integrability 1, then this behavior exactly appears. So in general, you cannot really improve this, but we know conditions under which you can improve it in the sense that you can put here on the right side the Kolmogorov widths in L2 instead of L infinity, which are smaller, yeah? And they are also much nicer to handle in general because then the best approximation is just the orthogonal projection, and you can deal with this more easily. So how can we put this? So for example, we can assume that the Kolmogorov widths in L2 have some regular kind of behavior, some polynomial logarithmic behavior with a main rate greater than 1/2. And then one can show that the linear sampling widths, they are of the same order always as the Kolmogorov widths in L2. Yeah, if you consider the error in L2. And then you can lift this somehow also to LP approximation under the assumption that these optimal subspaces Vn, they behave nicely in the sense that you have this Nikolsky type condition. So whenever these optimal subspaces or some near optimal subspaces for L2 approximation, they have this behavior that the uniform ratio of the uniform norm and 2 norm is bounded by square root of n. Then you get exactly the same result as before, but now with the Kolmogorov widths in the 2 norm instead of the L infinity norm. Okay, so what are examples that satisfy this strange condition? It's actually not so strange because, for example, you can take Sobolev spaces on compact manifolds. Yeah, then you have this condition, but also more generally, you can take the unit ball of reproducing kernel Hilbert spaces, which have the property that there is an orthogonal basis in this space H, and which is also orthonormal in L2 and which is uniformly bounded. So then you can consider the spaces defined by the Walsh system, Fourier system, Haar system, spherical harmonics, wavelets, certain wavelets at least, Chebyshev polynomials and such things. Yeah, I mean the Walsh system isn't precisely uniformly bounded, but it satisfies a weaker condition, which is also enough. So you can consider all such Hilbert spaces. Aha. And finally, in the end, I want to change the viewpoint a little. So what I did now is compare the sampling numbers with this Kolmogorov widths because it turns out naturally from our approach. But you might argue that it's maybe even more interesting to compare the sampling numbers with the so-called Gelfand numbers. What are the Gelfand numbers? Well, they are just defined like the sampling numbers, but this time we allow arbitrary linear measurements. So they reflect the minimal worst case error over the class F if you allow algorithms which use up to n arbitrary linear measurements. For example, Fourier coefficients or whatever. And if we now ask a question, how do the sampling numbers compare to the Gelfand numbers? This is basically the question, how good is information given by function values compared to information given by general linear measurements? And how do the results look like in this case? Well, again, I assume for simplicity some regular behavior of the Gelfand numbers this time. So we have some polynomial logarithmic decay here, and let's say the rate is large enough. So in all cases, if alpha is larger than 1, will be enough, but yeah. I don't show you the full generality now because it looks a little complicated then. But what we get for this regular behavior, interestingly, is that if either p equals 2 or p equals infinity, we can show that for any such class f and any measure mu, the ratio of the sampling numbers and the Gelfand numbers is at most of order square root of n. And there are classes where it is exactly of order square root of n, so this is best possible. So somehow the most you can lose if you restrict from general measurements to sampling numbers is to samples is given by this term square root of n. Yeah? And sometimes you can turn the square root of n into a constant under additional assumption. For example, if you can replace it by a constant if you consider L2 approximation on a unit ball of a reproducing kernel Hilbert space. For uniform approximation, you can also replace it with a constant in the case that you again have the unit ball of a reproducing kernel Hilbert space, but this time also with this boundedness assumption from above. Yeah, there's also a nice paper by Gang and Wang in this setting. And interestingly, here we compare, sampling numbers in LP with Gelfand numbers in LP. So this is a fair comparison, LP in both cases. But interestingly, we have no clue what happens in the case if p is not equal to 2 or infinity. Yeah, so in this case, we have only comparison of p here and infinity down here, or maybe 2 down here on some special cases. But in general, we don't know what happens there. So this is a very interesting open problem, I think. And that's already it. Thank you for your attention.
So I'm
just to double check what you said just previous slide.
Yeah.
You said that you do not know that if Gn in L2 and Cn in L infinity. Because if there is no Cn and there is Gn, that means the Kolmogorov width that we know that there is a constant on the right. But if you replace the Kolmogorov width by this Gelfand width, you don't know.
No, I mean if you consider the case where you have p in
2 there, 2 L2 for Gn,
yes,
and L infinity for Cn. Do you know that it's less or equal than a constant or not?
In this case, we know it's less or equal than a constant. Yes, I think. Yes.
This is my question.
Yeah.
Basically,
Yeah.
Because
Yeah.
for Kolmogorov width, you know that, but for Cn, okay.
Yeah, but the Kolmogorov widths in L infinity, they are smaller than the Gelfand widths in L infinity. So you automatically get this. Is it the right direction? Yes, I think, yes. Okay. At least for convex and symmetric classes F.
Yeah, you're right. You can
Yeah.
get it from there.
any other questions?
Thanks for a nice talk. So you had one slide with noise. I can't remember the slide number.
Must be the next one. Yeah.
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 So I was going to ask, is that sharp with respect to the noise? Because
Well, in general, yes. So you can construct examples where the estimate is sharp. Yeah. But maybe you can ask whether you can replace the 2 norm with something better here. But probably you can't. I didn't think about it too much. But
right,
in general,
so
the estimate is sharp, yeah.
say bounded noise, so eta k's will uniformly bounded, then this term would be blowing up as I add more samples?
Yeah, I think it should be sharp. I can think about it again, but it should be sharp, yeah. Yes.
Thanks for the talk. One other condition, could you remind me on the set D? Could you consider unbounded domain or even general metric spaces for D?
It's any set.
It's any set,
Yeah.
any kind.
Yeah.
Anywhere you can put a measure, lower measure, or
Yeah. If you consider the uniform norm, then it's any set. If you consider like approximation in the P norm, then it has. No, it's also any set. Then you just consider the spaces of bounded and measurable function, and it will work as well.
okay.
So you mentioned that so your result is for general space. I'm talking about the first half of the talk. Yes, about these points in infinity. For general spaces, you cannot get better than that. But for polynomials, for example, you can.
Yes.
What are other subspaces for which you can get better results, like for polynomials?
Thank you very much for my question.
Yeah, that's a very good question, which I don't really know the answer to. I mean, if you have spaces with better discretization results, then you can get also better.
Yeah.
Yeah, but I don't know how to characterize spaces where you have better discretization
There's the
results.
proof that you mentioned, use, for example, Nikolsky type inequalities, and I don't know whether for polynomials they will be any better, so.
Even I think depends on the domain. If it's a multivariate polynomials on a general domain, probably we don't know.
But there is some problems, because it's complicated terms that you take the Dirichlet kernel for the subspace, and now you consider bilinear approximation the special kind of the Dirichlet kernel. And in those terms, we can give the answer, but it's just a sufficient condition for upper bound for discretization.
Yeah.
Any more questions? David is very efficient, so we can still ask a few more questions. We still have some time.
Yeah, so what happens if you take the eigenfunctions of the Laplacian on some domain, the span? That would be somewhat canonical space.
If you take it, if the domain is some compact manifolds, then it will work beautifully, because then you have precisely this kind of.
The general result or a better result?
You want different domains.
No, the square root n. Can you do better if you take special space, say span of eigenfunctions of Laplacian?
Well, not in this Nikolsky condition, of course.
No?
But you mean for this discretization here?
It depends also on Bernstein inequality. If you have Bernstein inequality, you are lucky. And in many cases, you have them.
Yeah.
Charlie, basically there is no hope, because if you choose like randomly trigonometric functions, then the lower bound will be square root of n divided by log n. So that means it could be a little bit better. This is what we have with Boris.
Okay.
So, yeah, but if it is something specific, like some extra assumptions, then probably you can do. Or like, for instance, trigonometric polynomial concepts. You can do it. Other than that, it's...
Any more questions? Questions? Let's thank David once again.